Everyone, it's my honor to present Gaurav Sukhatme, our speaker today. So Gaurav is professor at UC in CS and ECE, correct?
That's right.
Got bachelor's from IIT Mumbai and then stayed at UC for master's and PhD.
That's right.
And yeah, I mean, he has a long list of honors that I'm not gonna read. He also was one of the founders of RSS conference. And yeah, he does research in what he's going to be talking about today, multi-group, multi-agent, quadrocopters, but also in robotics and robot manipulation. And yeah, always very, very interesting work coming out from his lab. And my personal note is I told him today, I saw a presentation. He visited us when I was doing my PhD in Germany, and he gave a talk, kind of like a related topic. Well, not that related. It was a submarine robot that was coming out, in and out, and has to be kind of like well done so that it can get information that it needs coming up because it was costly to come out of the water. It got me in a rabbit hole of exploring active learning and how kind of like probe in the right and more efficient way to get information that then I use in one of my papers during my PhD. So yeah, that was amazing. So maybe you can get also something useful for you during his talk, hopefully. And welcome, Gaurav.
Thank you so much. Thank you, Roberto. And thank you, everyone, for coming. I just learned 5 minutes ago that there are no cookies, so I'm even more gratified that you are all here. That's a testament to your interest in robotics. I'm very happy. So what I'll do today is I'll tell you a little bit about a line of work in my lab that began several years ago, began about 7 years ago. I'll give you a little bit of the precursor work that got me thinking about these problems, and then tell you about some of our most recent work in the area. At the end, I'll point to a few papers that we've written in topics connected to the work I'm talking about today, but I'm not going to be able to cover all of those today. So I'll stick to a main line of work, and then there's some other work you may be interested in, and I'll draw your attention to it. So this is a robot platform that I want to focus on today. Many of you have experimented with this platform. You know it well. And for those of you who haven't worked with it, it's a small robotics testbed of the Crazy Fly. It's an example of what I would consider highly resource-constrained robotics. It's tiny. It weighs very little. There's no GPU or anything like that. It just has a small CPU. A tiny amount of memory, stays in the air for a few minutes at a time. It has a nice IMU actually for its size. And lots of multi-robot people use 10, 15, 20 or more of these as a good test bed. And I know several of you here have done the same. It's great for student projects as well if you're getting started, right? So it'll just be my running thread. Like, this is when I say resource constrained, I want you to think about this. All our experimental results will be on this particular one. So I just wanted to take you back a few years, about 8 years ago. So this was work jointly done with Nora Ayanian's group when she was at USC way back in 2017. And the task here was, there's a group of these quadrotors. They begin in some known locations, and there's some set of obstacles along the way. We just want them to end up in some pre-specified end goal positions. That's the entire task. And we want this to happen. Where they don't run into each other, where they don't run into the environment, things of this type.
But it doesn't matter which one goes where.
It does matter. So this was, in fact, designated locations, right? So, and they were perversely picked for the experimental conditions. So yes, sort of. And in my life in 2017, to me, this was a fast planning and replanning problem. Like, to me, it was like, and just to Nora and I, it was like the problem sort of plays out like this, right? So there's some initial placement. You do a discrete plan, which is labeled and anonymous, and then you refine this plan over time, right? And this is clearly, you've got to do some smoothing. You have to do a few other things. That you need a fast solver to do this online. This is a bunch of interesting stuff, right? And there's some interesting sub-problems that we solved along the way, and we ended up building this whole pipeline out, and it worked pretty well, so on and so forth. And it appeared in a string of papers, right? And actually, there's some interesting has some interesting properties to this. The planner ran fast enough that we could do this for much larger scale environments than the one I'm showing here. So we had some results on doing this, in an imaginary environment, which could be, might be a warehouse or might be a city block or things of this type, right? There were some other complexities about what if the robots fly on top of each other and how do you plan for downwash. And we added constraint after constraint and developed techniques to make the solver still run on top. Right? That's kind of the way I thought about these problems, right? And then one of the questions that naturally came up was, can you solve exactly this problem without planning? So can you, in fact, learn a controller to solve this problem, right? And remember, this is 2017, so this is not today, right? I suspect many of you live in a world where your first solution to any problem is to learn the solution to the problem, but that was not my world in 2017. And so the question we asked is, can you learn a control policy for a group of quadrotors? And the constraints we want to put on this are that we want to map the observations the vehicles make directly to motor thrust. So your learn policy actually flies the vehicles, not some abstraction of the vehicle. And the goal is the same. Can they approach targets while avoiding collisions, right? The little video down there says that the answer is yes, you can do it. And in fact, this talk is largely about a family of learning problems that flow from this question, right? So it won't be about planning. It will be about, can you learn this, right? And so, well, our question really was, can you do this? There's a little twist that we put on the problem. And the added twist was, can you do this with no physical demonstrations whatsoever? So you're not going to do any training on hardware. All the training is going to happen offline, right? Not on. And why we became interested in this problem was because we thought that a learned controller might exhibit more agile maneuvers than our typical planned techniques of doing so. This is sort of unverified hypothesis at the time. But we were conscious, and this is already well known, even a decade ago or more, that you could build a lightweight simulator for vehicles like this, but it's going to be a pretty approximate version of the actual physics of the system. And so there's this potential for a fairly big gap between what you're simulating and what actually happens. And so this constraint of not having any physical demonstrations might end up defeating us. So we weren't quite sure at the time whether this was surmountable or not. So we began in 2019 by doing this just for one robot. So we demonstrated that by training offline, we posed it as a reinforcement learning problem, that we could do attitude stabilization and trajectory tracking for a single vehicle. And it was capable of rejecting some fairly significant disturbances, as you can see in this video. There's no multi-robot work here. There are no obstacles in this environment. The robot's just servoing to a known location. And if you disturb it, it tries to get back there, right? That's the entire task. But we thought this was a reasonable basis task. If you could learn this, maybe there's some hope to learn the more complicated thing we want, right? And this was Artem's work as part of his PhD thesis. So today is really the problem I posed, which is what if you have a multiple quadrotors and you want collision avoidance, you want direct thrust control, you want to be transferable to real robots, you want this to be robust. So if I inject disturbances into the system, you want good recovery behavior. We also want at inference time the learn policy to run on these vehicles. And so by definition, we want to be able to make a forward pass through the learn policy very quickly, and it needs to be compact in size so we can squeeze it into a few kilobytes of memory, right? So that's where the small constraint comes in.
What assumptions are you making about mutual awareness or communication among the robots?
Yeah, I'll say that in a second. The early experiments were done in Vicon. And so globally, every position was known to the vehicles. We've relaxed that since, so we do onboard position estimation, and we actually don't do any inter-robot communication. So the learn policy functions as each robot on its own. And so, as I mentioned this earlier in a couple of conversations, this will be one of those things where I will show you videos in the end of this thing working. But we have to be very careful about saying, this is the robots are coordinating with each other, right? They appear to execute coordinated behavior. And Peter has written about this extensively, and so have other people. So I will try and be very careful about not using phrasing like they learn to coordinate. The robots learn to navigate in a way where they don't hit each other and they don't hit anything in the environment. And the net effect is that they appear to coordinate with each other, right? That's actually what I'm saying.
But they aren't all getting each other's approximate location.
Yeah,
So
they'll,
so it's not that they're just using,
and not all, but only a small neighborhood.
okay,
And that's going to be one of the key things. Because otherwise it's a little indefensible where if you say, all states of everybody else are known, what are you really going to do beyond 7, 8 robots, right? So not all, but just a neighborhood. And I'll have something to say about the size of the neighborhood.
Good.
Yeah, Volkan.
But you need more to specify the end goal, right?
Yes. So what you really need here is the difference between your state and where the goal is. And so the goal is known in global coordinates to all the vehicles here. And when I say that they are running a state estimator, all of them are estimating their state in that same global coordinate system. So they're all initialized appropriately in that global coordinate system.
So the task is like go to your goal while the.
Correct. Exactly.
but they do that, I think you said they each have their own individual goal, it's not there's a set of goal.
Correct.
around them.
Correct.
Okay, that's not right, yeah.
So the computational problem, even if you ignore all of the low-level robotic stuff, right?
Yeah.
It's a multi-agent pathfinding problem,
It is.
which is NP-hard,
It is.
and you're still able to learn something that solves it.
Yeah, you'll see. You'll see. The key missing word on this slide is the word guarantee. That's the reason, yeah, right? I couldn't possibly give you a guarantee because of exactly the reason you said, right?
So simulator is for the crazy flying.
Excuse me?
So simulator is for the crazy flying.
Yeah, it is. And if you like it, you can have it. Yeah. It's free of charge. Okay, so the way we formulate the problem, yeah, question in the back.
So we could, you have now a certain number of drones.
Yeah.
Each one is reaching a goal.
Yeah.
And you're doing the dynamic of something.
Yes,
Okay.
correct. That's exactly right. Exactly. And so each quadrotor just sees the rest of the world as its environment, whether there are other quadrotors or static obstacles. There's nothing particularly fancy about that. Let's just step through exactly the questions presage this. So the state for each quadrotor is its relative position between itself and its goal, its own velocity, a rotation matrix associated with its roll, pitch, and yaw, its angular velocity. And then it also sees the relative position and relative velocity between itself and k closest neighbors, right? Where k is obviously a hyperparameter of some sort. So you have to pay some attention to k, because if there are n quadrotors and k is on the order of n, then this isn't much of a coordination problem. But if k is small relative to n, then maybe we've learned something new.
So it's the set of closest neighbors same all the time.
It is not.
So you have to do the monitoring, make sure that keeps.
It is not this.
Right.
So there's some k neighborhood that are the closest, right? And this is dynamic changes, right? Obviously, it's a bad illustration because it's a very large neighborhood relative to the number of robots. But I'll show you examples where that's not true.
So what kind of sensory data do you need to?
I'll tell you in a second. Yeah, I'll tell you. Yeah. So the action space is small. It's very low dimensional. Each robot generates four actions that directly control its 4 propellers. And these are normalized for a variety of different reasons and so on. Okay. So now I want to train offline. So I need some kind of training environment. I need some kind of gym in which I can do this training, right? So we built our own little lightweight simulator for this. It's a very simple and fast simulator of the rigid body dynamics of a quadrotor, right? So it's sort of textbook simulator, right? There's no aerodynamic effects, there's no coupling, there's no downwash, there's no non-rigidity of the blades. This is like the simplest model you can write. And we essentially integrate these equations forward in time, which is our simulator. Right? Now, so that's the physics we simulate. But occasionally in simulation, when you're learning, the robots are in fact going to collide with each other or run into the environment and so on. So we need some kind of collision model, right? We need to do something in simulation. Now, we're going to pick a very idiosyncratic collision model. Our collision model, which I will describe in English because it's kind of really idiosyncratic, goes as follows. When in simulation, when two robots collide, we will set their velocities pointing away from each other, drawn randomly from a distribution on one side of the plane of collision and the other side. And so they'll just ricochet off each other, and we'll randomly pick the direction in which they ricochet off each other, right? This is not just a first order model of collision. This is, a physicist would tell you it's not even a 0th order model of collision. It conserves neither energy, momentum, or any quantity that's physically sensible. It just sort of resets the world, right? But it doesn't reset it completely arbitrarily, in the sense the positions of the vehicles, the split second after collision, are faithful because the vehicles don't randomly teleport to some random location, but the velocities are not faithful to any physics, right? They're faithful in the cartoon sense of the word faithful, right? So even saying this is a 0th order model of collisions is a little bit of a stretch, right? So it's a very idiosyncratic choice. So there are a few things you all have asked me which are more straightforward, but Peter's question on neighborhoods, I need to come back to. The choice of neighborhood is important, and how it scales is important. And the second is, what impact does this idiosyncratic choice have? And why is this a good way of doing this? Because some of you will say, you have a bad sim to real gap when you began. You've just made it worse. So how is it reasonable in offline learning to deliberately worsen the sim to real gap? That doesn't seem to be the kind of the modern trend in doing it. But I have some reasons to believe it's a good thing to do in this setting. Okay, and then I need some kind of training environment. So what we do is in training, we just design a bunch of arbitrary shapes. These are just hand designed, and we scale them in size. The dots are colored because the blue robot is supposed to go to the blue dot and the yellow robot is supposed to go to the yellow dot, and so on. So when I instantiate these, the robots are supposed to go to their own color. And I'm going to instantiate these at various sizes. I'm going to make them bigger and smaller. I'm going to change them rapidly. So I'm going to cycle through, go to this shape, then go to the other shape that causes them to fly from one location to the other. Also going to do a few things that are a bit harder. Maybe occasionally I'm going to pick the same goal for all the robots, so they're all told to fly to the same goal. This induces collisions, and so ideally they learn not to collide, things of this sort. So I won't go into all the details. There's also a pursuit-evader task where robots are trained to all fly to the same location, but that location moves around. So there's a whole slew of these training environments. So I know how to simulate the physics of these things crudely. I know what kind of training regimen I'm going to put them through. I need some kind of reward because almost all the fun is in the reward design. So we're going to reward to minimize the relative distance between the vehicles and the goals. You want to reach your goal. That's an obvious one. We're going to penalize collisions, right? But we're going to penalize collisions in this interesting way, where there's no penalty far away. There's a penalty for being near other vehicles, and then there's a very high penalty for the actual collision. So this is also not completely untraditional. Significant number of people do something similar, but we're only going to do this over the neighborhood. So we're not going to do this for all vehicles. We're just going to worry about your K nearest neighbors. So this K pops up here as well. And then we inherit the reward design from the single quadrotor stabilization problem, which is the first video that I showed you, right? So this is just that if you have arrived at a location you want to be at, you want to hold that pose stably.
So you call this reward design. So how hard is the design of this? How sensitive are you to the alpha values and like all of these different terms?
Yeah,
or is this the first thing you tried?
Yeah, we have some reports on sweeping these parameters. They're not terribly difficult to arrive at. And it's not at that big a space considering modern rewards in many settings. I'd say I'd say they fall prey to the standard sort of trial and error technique. There's not a good principled way of solving them, but their ranges are generous. They're not particularly difficult to do. And of course, once you figure them out, then you don't change them. So they suffer from the same problem that many RL techniques suffer from, which is they are hand designed. Though whenever my controls friends tell me that, no, look at this is crazy, right? You more or less wrote the task down here, right? I tell them, well, yeah, but I mean, when you write a cost function for something, you more or less also do the same thing. And so this is a challenge.
But I guess I asked partly because like often when you think about reward design, there's the actual thing you care about, and then there's
Yeah.
the shaping terms.
Yeah.
And so like, is there a sense that some of this is the actual thing you care about, and some is the
Actually, it's a good point. This is almost exactly the translation of the task, right? The first term is, did you reach your goal? The second two terms are don't collide. And the third terms are stable flight. So they're very much, there are no proxy terms really of any kind.
You can actually interpret it as the logarithmic multiplier.
You can. Yeah, you can. And I suspect this is not carefully written. We can eliminate one of them, of course, by dividing just. Okay, so some details. So now we need some sort of, now we do the conventional thing. We maximize the expected sum of discounted rewards. And now we play around a little bit with the underlying model architectures. By the way, we will use PPO for everything we do here. And since I'm not much of an RL expert, it'll be a vanilla implementation of PPO, right? So on that axis, I have nothing novel to say. Right? There are a few things one can do there too, but throughout this talk, there will be nothing novel to say about that, right? And we will in fact deliberately not change anything about it. So one way we design the network to do this is like this. We're going to have two encoders. The observations of the vehicle's own state go into one encoder, and the observations of the neighbors, relative observations to neighbors, are going to go into another encoder. And these two are going to get combined, and there's going to be a decoder that's going to generate the actions. So that's one architecture. And one way we're going to do this is we're going to pretend that all neighbors are alike. And so we're going to do some permutation invariant thing with the neighbors. In this case, we're going to just take the mean, right, which is a permutation invariant operator. And the encoders are small MLPs, so these are relatively small networks, and we're not doing anything particularly fancy here. So that's kind of one way of generating the system and working with it. The problem is, of course, it doesn't convey the relative importance of different neighbors. So everybody who's near you is sort of alike. If somebody's flying towards you at high speed and the other neighbor is the same distance away but not flying towards you at high speed, this setup doesn't really distinguish between the two. But it's a lightweight setup, run fast, so we'll see how it goes. The other way of doing it, there are many ways of doing it, but you can do something that imposes an attention mechanism on your neighbors and train the network to actually attend to the neighbors that are somehow more important, right? And the neighbors that are more important are the ones where the gap between your state and theirs is closing more rapidly than the others, either because they're moving towards you or you're moving towards them or both, in a way that is not happening with the other neighbors. So you can learn that. And maybe this is the world's tiniest attention mechanism sitting on this vehicle. So we do essentially the same thing. We have an encoder for the state of the vehicle, but instead of just doing a encoding of the K neighbors, we also learn K attention scores. So which neighbors are more important than others. And we combine those and we generate the 4 actions on each vehicle. Recall that in the end, this will run on each vehicle, right? So each vehicle has state inputs and each vehicle generates 4 commands to its. Yeah.
So the state input, okay, the information is from where?
Yeah, so I'll show you one round of results where the state input comes from Vicon. So the positions are measured because there's a motion capture system and we have global positioning because of it. At the end of the talk, I'll show you videos where we relax that, and we now have an onboard position estimation system. And so we are not tied to Vicon, and each vehicle is doing its onboard state estimation. And so runs pretty robustly.
So do you use something like the Lighthouse?
we do ranging using range sensors to obstacles, and we look at flow looking down optically. Those are two. So these two techniques, you can compare them. You can also compare against a blind system where there is no notion of neighbors at all. And so there are three graphs here. This is all training time. So you see simulation steps of training on the x-axis. We train for about 1 billion steps. On the first picture is just sort of, if you do this style of work, you always have a graph that shows total reward. It always irritates me because all it tells you is that you built a good reward accumulator, but we built a good reward accumulator. So you can ignore the picture on the, any RL paper that ends with that graph is useless because, I mean, you can build good reward accumulators that don't achieve the task. And so that's not the point. In our case, we do achieve the task. So the other graphs have meaning. The middle graph actually plots the average distance to the target. And you want that distance to go to 0, right? So you want each robot to reach the target. So in the beginning, it's not very good, but as the robots get better at flying and navigating, over time, you can see that the average distance to target shrinks quite a bit. It doesn't quite go to 0, but it shrinks quite a bit. So there's some progress. And then the picture on the right shows what fraction of the training episode do the robots actually stay in the air. Because remember, this is a system where the vehicles begin not knowing how to fly. So they have to learn how to fly, and then they have to learn how to navigate, and they have to learn not to hit anything, right? That's really the whole task. And so this plots what fraction of the episode they stay in the air, and you want that number to be close to 1, right? So they do pretty well. But it turns out that, so collisions are rare. By the time things settle, you get very few collisions every few million training steps. Not 0, but very few. But it doesn't seem to matter that much whether you use whether you attend to the more important neighbors or not. I mean, these graphs certainly don't suggest that there's much of a difference. But in fact, it does matter because you should look more carefully at what task you're asking the robots to do. So let's pick a challenging task like pursuit evasion. So this is a task where all robots are told to navigate to the same goal, and that goal whizzes around. So the vehicles have to, in some sense, they're all servoing to the same position in time, right? And here you can see that attending to your important neighbors, which is the lowest curve, actually gets you the fewest collisions, right? So these things separate out if the task is challenging. And so the previous graphs are a little misleading. It's important. So a lesson which many of you, I suspect, know is that if you have an RL method trained across diverse tasks, averaging across tasks is fraught with difficulty. Like it doesn't quite reveal. You can mask poor performance, and you can sometimes, in fact, shoot yourself in the foot because you, in fact, have something good, you just don't see it, right? So averaging across tasks is not a well-founded operator. You have to be careful about it. You can see here's an example where all vehicles are told to navigate to the same goal, except that goal sits statically in one place. So they're all told to go there, right? Now, of course, if they all actually go to the goal, you'll get collision. So what ends up happening is they end up orbiting the goal at some standoff distance, right?
So it's the initial state,
or all the vehicles? No, it's randomized every time.
So it's randomized.
Yeah.
Initial state
Always.
Randomized.
And so, yeah, so if you look at the attention weights, you'll actually see that closely located, fast-moving neighbors, you tend to attend to them more. And you can look in the network and you actually see that the attention mechanism has meaning and works pretty well, right? So now let's look at this business of what happens if you have more robots. What if you have more robots? And so on the x-axis, I'm going to plot how many robots there are. And the numbers here are all drawn from testing in simulation. So these are not results on flight experiments. I'll show you those in a minute. So there's a fixed room. It's 10 by 10 by 10 meters. It has walls, so you don't want to collide with those walls either. And what I'm going to do is I'm going to plot on the y-axis the number of collisions, but I'm going to normalize them by how many robots there are. and how long the flight episode lasts. Because it's sort of unfair to compare a short flight episode with a long flight episode and just count the number of collisions. And also, if you just have 2 robots or 20 in a closed environment, it's not quite the same thing. So I'm going to normalize for those 2 things, right? And so there's this normalized index on the y-axis. You want the number on the y-axis to be as small as possible. You don't want it to grow as you grow the number of robots, which is impractical. So the real point is you want it to grow as slowly as possible as you grow the number of robots, right? Okay, so let's look at this picture, which is the little star that's labeled pre-trained. So this is a pre-trained network, which was trained with the assumption that n equal to 8, i.e. there are 8 robots, and k equal to 6, that is, each robot gets to count 6 robots as its neighbors. So this is an extremely generous way of doing things, because if you have an 8-robot system and each robot counts 6 robots as its nearest neighbors, it's only not paying attention to 1 robot, right? So it's pretty generous. It isn't quite the state you want to end up in for a real scale system. But we'll be generous and we'll call this our pre-trained system. So we'll train a network that gets good at solving this 8-6 task. I'll call it the 8-6 task, right? And what I'll do is I'll run it where there are, in fact, 8 robots. And you can see you get very few collisions because that's what I trained to do, right? It's very good at that setting. But now I'm not going to change the network. I'm not going to retrain. But instead, I'm just going to make the number of robots 16. The network was trained as though the robots believe that there are 8 robots and 6 of them are neighbors. But I'm going to now test with 16 robots, and the neighborhood size is held to 6. And the system works quite well, actually. You can see that the number of collisions goes up slightly, but it's not a complete disaster. But then if I keep the same network and I make the number of robots 32, you can see the number of collisions goes way up. And in fact, by 48, we go off the chart, right? So you can't just take a network, even a very generously trained network, because it was trained for 6 neighbors, and in fact, extract more mileage out of it without changing something. So the natural thing, of course, is why not do some fine tuning, right? Why not have an 8-6 network and then allow a little bit of fine tuning? So when you go from 8 to 16, you permit maybe 200 million additional steps of training, right? And that's what this lower graph does, right? So you can see that it scales a whole lot better if you allow 20% additional fine tuning. So it scales pretty well up until a point, and then, you know, at some point it breaks, basically, right? And of course, what you can also do is you can just train a neural network from scratch for each setting. So this is the blue line here, which is, you know, solves the 8-6 problem, then the 16-6 problem trained from scratch, then the 32-6 problem trained from scratch, and so on and so forth. And this point reflects a trained network that is solving for n equal to 128 and k equal to 6, right? And that beats everything else, as you would expect. Of course, then you have to retrain from scratch each time, right? So there's some cost. So on the other hand, the encouraging result is if you are willing to train from scratch, you need extremely small neighborhood sizes for large networks. So you can have 100 robots and you only need to pay attention to 6. As long as you're willing to train for that regime, you can get extremely good results out of the system.
Biological evidence is that birds pay attention to 7.
Yeah, we swept that and somehow ended up with 6. We swept from 3 to 10, I believe. I mean, you end up with a decimal number, so but it suggested 6 to us. But yes, there is evidence for there may be some robustness reasons. There may be so many other things going on. I think in our paper, we actually have one line that says we're close. We don't have any kind of explanation.
There's experiments on fish and
there is, yeah. Experiments on fish, yeah.
Do you have any intuition what's learned during fine tuning? Like, I've learned to pay attention. I might naively say, if I'm paying attention to my 6 neighbors, why doesn't this scale infinitely? But of course, I've been in like a traffic jam before.
Yeah.
So I understand that. But what is it I'm learning in a fine tuning stage? Like, is it my impact of me and my 6 nearest neighbors on the rest of the swarm? Is
Yeah.
that-
We think that the increasing size is really increased difficulty of estimating the reward function. That
The
we
global reward.
correct.
Even though your.
Even though
reward
your reward is close by,
because you're measuring here a global.
we are. So we think that may be the reason, but we're not entirely sure. Yeah.
It just means that like each robot has like a 1% chance of crashing, and then 100 robots have like a combined of like 2% or something.
Yeah.
Like purely because of more robots, not
Purely
like-
because of more robots, even though we normalize. Yeah.
So when you're training with more agents, when you do the update with BPO, are you rolling out, let's say, 128 steps for each agent in the sim? And then you update all of those agents because they have some network and you just use that as your batch. So when you increase the number of agents, you're effectively just increasing your batch size. So now you have fewer policy updates, right? So how do you deal with that or affect that at all?
We do, and actually we do some clever interlacing, so we don't do batch updates in the same way that you described. There is a very nice pipeline under the Spark sample factory that Alexei Petrenko wrote to actually be relatively fast, so the training times don't scale poorly as you add agents. So if you're interested, you could look there. There's a paper that describes it that was at ICML a few years ago. And it'll give you the exact details on how we do this. So it's not quite the implementation you have in mind. We don't actually do full rollouts in the way you described.
Gaurav, did you say it, but I didn't get it clear. What is your intuition why pre-training plus fine-tuning works until 64 and then
Okay, yeah.
from scratch kind of like stays more stable, or you don't know?
I don't know.
Okay.
Yeah. So the question is about this kink here, right? So we don't
Yeah.
have I don't have a good explanation for.
Or even the difference between from scratch and pre-train is just because the problem is more difficult to train from scratch, because in convergence you would say hopefully both would converge to the same thing. It's just a matter of little data for the from scratch, or it's just that the starting from scratch makes it more difficult?
It's difficult to know. I don't
to
actually don't know.
Okay.
It's a good point. I don't have good intuition for that.
So if you take the virtual model from 128.
Yeah,
agents,
yeah.
Then put that to 8 agents.
Yes.
What's happening?
Actually, I don't think it works as well was our result. I think it works less well than the 8 cells.
So it's basically cannot like generalize. It can generalize to 8 agents, but not that well.
Correct. Yeah. And so, in simulation, this is what it looks like. I mean, you can test in the same environment where you train, and the colors correspond to the vehicles. So each vehicle has to go to its own color, basically. You can set goals and the robots fly there and so on and so forth. And so if you like the simulator, play with it. You can use it for training. You can use it for testing, a bunch of other stuff, right? If you tell all the robots to fly to the same goal, they end up doing something like this, which is not an unreasonable thing to do since they aren't supposed to collide with each other. So there's some learned trade-off between actually achieving the goal versus not hitting each other. There are multi-robot people who'd say this is emergent behavior, but I will just stay away from anthropomorphizing it. This is what it's encoded in the reward function. So you get sensible results, I think. You can in fact deploy these, and so here's a deployment on vehicles. There are 8 vehicles here. They're told to go from a 4x2 grid to a 3x3 grid to a circle to a 4x2 grid. Pretty well. It's a tiny number of network parameters. It's about 6 kilobytes worth of neural network. It's very, very small.
Do you ever run into situations where because you're asking each of them to individually optimize for its behavior, but there could be a situation where one optimizing slows down all the rest or something like that?
It can.
Played with
Yeah, it can. And there are some interesting. So this is older work that I'm showing you. We're about to send off a somewhat different way of architecting the network where we can do things like where we think we learn things like a robot deliberately waits for another robot to go through a barrier and then chooses to go. Again, that's what it seems like to the observer, but you can now also observe behavior of that type.
I mean, because there's a whole body of work that explicitly optimizes the make span.
Correct.
To get everything
Correct.
there as quickly as possible.
Correct, which we don't.
That's not there at all.
That's not there at all.
Have to be.
Yeah.
Coincidence.
They don't. Yeah,
Okay.
exactly. Yeah.
So maybe you're going to show this, but how does this compare to like formation control with?
Yeah, I'll show you some comparisons with at least a couple of places. There are many bodies of work. I'll compare with a couple and you can see what. So now the other thing, I talked about K, the size of the neighborhood, but what about collisions, right? So here is the system actually flying the learned controller, right? And here's a snapshot of occasionally what happens. And if you look closely, you'll see two vehicles collide, then they bang into the floor, then they recover, right? And occasionally we collide, and not always, but very frequently after collision, we recover. That is the main advantage of simulating collisions the way we do. The worst thing you can do when you're learning offline is to end the training episode because you collide, because then you'll never learn to recover. The second worst thing you can do is to obsess over the physics of the collision because you have no hope of writing a good model for it. Not when articulated objects like this collide. These are not spheres, right? So that's number two. The best thing you can do is to have some sort of crude model that puts the vehicles in unexpected states that are not completely made up, as in the vehicles are still where they're supposed to be. Their velocity vectors are definitely kind of made up. But what the vehicles learn to do is to recover from states that they wouldn't otherwise see. And there's tremendous value in doing that, right? So it's one straightforward example where increasing the sim to real gap actually bears fruit. Right? It's not a generalizable statement, can't say that about all our problems, but this is one case in robotics where running towards danger may be the right strategy, not running away from it, right? So it was an unexpected thing for us.
It's a domain randomization.
It is a domain randomization, actually.
But you could imagine them in simulation learning to exploit
collisions. Exactly.
As long
Right.
as you make it unpredictable enough, then they can.
Then they can. Yeah, exactly.
But I don't think it's even too different in manipulation. I remember Karen Liu also saying the same.
Yeah.
Like, I want to make my simulator less realistic so that it's more realistic.
You can get some mileage in other settings as well. Yeah.
But wouldn't you get similar behavior if you just use the stabilization controller for the single quadcopter that you showed before?
You can. It's in our reward function.
Right.
So it's learning. But the important thing is, can you learn to stabilize from initial conditions that appear sporadically and infrequently in your training data?
Yeah.
And so you want those to appear. And in fact, later I'll suggest that what you really want to do is during training, you want to keep a replay buffer around. So states leading up to a collision, you keep in your replay buffer for longer. And that way you quickly learn how to recover from collision. So in fact, in our modern incarnation, that's what we do.
But I guess if you just make these quadcopters bigger,
Yes.
then you won't really recover from
Yeah.
collisions anymore.
Yeah, that's why you have to be super careful, right? Like I can't walk around saying collisions are great for any robot. Let them collide. I mean, we're exploiting the properties of these lightweight things. They mechanically are geared for this, right? So yeah, there's definitely that, right? Somebody asked about baseline comparison. I mean, look, one way to not collide, if you want to go from A to B, is for each robot to just compute some safe region in which the other robots are not, right? And there are many papers that follow this line of work, right? So this, for example, from Max Schwager's group, is this idea where each robot just continually computes a collision-free area for itself and does short horizon planning within that area. Comes with a guarantee of no collision. And the robots eventually will reach their goal, right? That's very much a good thing. So you can implement it. So on the left is a implementation of the robots computing Voronoi cells and not colliding and switching goals. And the right is our system, right? Maybe you can tell in the video, or maybe you can't, but they're a little, our system is a little wonky. It's the one on the right, right? So the upper graph is velocity on both sides. The lower graph is acceleration on both sides. The x-axis is time. The two panels on the left are Bernoulli cell decompositions that are being calculated online, and the one on the right is our controller. You can see we fly with significant acceleration and velocity peaks that the other system doesn't. And we tend to get to goals much quicker, but there's no free lunch. The system on the left comes with a guarantee, and our system doesn't. Right. So it's important to point out that they're solving the same problem, but there's a guarantee in the case of PVCs, and we don't provide a guarantee. But we end up with some interesting behavior, and you end up with very few collisions in our case, and even in the few collisions you get, you recover from them. So the gap between us and the guaranteed system in practice is not as high as you might imagine. Still, it's important to point out that there is a guarantee. You can also do clever things like toss a beach ball into a bunch of these, and they'll fly away from it and so on. This is just yet another obstacle, but that's sort of a gimmick, right? So far, I didn't show you anything with real obstacles. We can do this with obstacles in the environment. I will now go a lot more quickly so that I'll finish in 10 minutes. We can essentially run the same system, but in environments where there are obstacles. We're going to have an encoder that encodes for obstacles. We have experimented by doing this in a couple of different ways. We have 3 encoders, one for the vehicle itself, its own state, one for the relative state difference between the vehicle and static obstacles, and a third one for the moving obstacles. We've also experimented with having just 2 encoders or having 1. So there are a variety of incarnations of this. If you're interested, you can read the paper. But this works in reality. The observations and so on are here. The range sensors come into play. So the observations include range measurements to the obstacles. We use a local sign distance field to encode these. And so, for example, this is what version 2 of the system looks like, where there's a self-encoder, a neighbor encoder, and an obstacle encoder. And then there's a single multi-head attention module over the obstacles in the environment, and the results are concatenated into a single latent, which is then decoded to generate actions in the vehicle. And this works quite well. We also do the replay buffer idea that I mentioned briefly. So you want to amplify collision events while learning. So if states lead up to a collision, you want to hold them in the buffer and expose the system to those states more frequently, so that you quickly learn not to collide. I'll skip over the results from this. There's another comparison I wanted to illustrate. We also compared in environments with obstacles. When we compared with the Voronoi cell method, there were no obstacles in the environment, no static obstacles. You can also compare with barrier certificates, SBC, for example, or with glass, which is a synthesis of planning with end-to-end learning. What we're plotting on the x-axis is the size of the obstacle, and what we're plotting on the y-axis is success rate. Success means that the robots get to their goals. So you can see that what ends up happening with our system is that as the environment becomes more and more crowded, our system tends to succeed more frequently. Whereas environments like barrier certificates, which are guaranteed to not collide, will slowly start to not succeed, because there will be no guarantee you can give if the gap is too narrow to fly between 2 obstacles. Our system will fly between those obstacles, sometimes will collide, occasionally will recover from those collisions. But if you measure aggregate success rate, we will actually do better than the method that's guaranteed not to collide, right? And so there is a real issue here. There's a family of methods that are guaranteed never to collide with the environment. Barrier certificates is a great example. But they are also conditioned on the idea that you're willing to give up on achieving the goal. You see this if you do self-driving cars. If you never want to collide with another car, the easiest way is to leave the car parked in the garage. It's a foolproof guarantee, right? But then you also don't get to work. This is the central problem with guaranteed approaches for safety. They are at the bottom, at the deep down, they are not performant. They're not performant when it matters the most. They're performant when certificates are easy to provide. But the cases I care about are precisely where certificates are not easy to provide. And there, robotics needs to take a slightly different view of the problem. So this is my view of how one should look at the problem, right? So don't confuse no guarantee with bad, right? That's not robotics, right? Okay, stop pontificating on that a little bit, right?
But it all depends on the nature of the guarantee that you're providing. Right?
Yes.
I'm not saying that certainly the providing guarantee doesn't always make a system performance, right?
Yes.
But you don't provide any guarantee at all, but
Yes.
sometimes you run into big trouble.
Of course,
Right.
of course.
So the real question is, okay, how do you actually stack your system such that you can have a balance of?
Of course, no question. Yeah. Sorry. Just to show you that you can do this kind of thing in the lab. So, that thing had maybe 1,800 parameters, runs completely on board a quadrotor, very, very small now, right? Now I have like 3 minutes left. So I want to say two more things, right, quickly. We have a new line of work on saying, what if you take these learned controllers, can you actually make their behavior safer? Not guarantee safety, but can you make them even safer than they are now? So what you can do, so one approach that we've been playing with recently is you freeze the learned system and just take that last latent representation before you decode. Can you actually edit the activations of that latent by predicting whether that latent is encoding a state that's likely to lead to collision? So we learn a network that's able to do that. And now what we are able to do is, if that latent is determined by a classifier to be likely leading to a collision in the future, we essentially edit that latent and replace it. But here's the kicker. We replace it with a latent that encodes a less safe state than it is in now. So in other words, this is the oldest trick in robotics. You fool the robot into believing that things are even closer than they're supposed to be. So if you feel that you're encoding a state that's likely to lead to collision, you replace the encoding of that state with an encoding that's actually signaling more likelihood of reaching to collision. And you take the frozen controller and let it run with that. You do it for like a certain number of states, right? So this is an approach that we've been playing with. Again, not a guaranteed approach. It's a activation editing approach. We've just submitted it recently. Has pretty good results. So if you sort of look at it, this is with this sort of latent editing going on. You'll see we get collisions with this latent editing. We're able to also prune out the kinds of collisions our system gets. So we're trying to sort of slowly compress. We're going from a system which collides infrequently to even more infrequently, coupled with recovery from collision, to really squeeze this to a point where the number of collisions becomes very, very, very small, right? So that's one line of work. We have more challenging tasks where the robots have to cross each other and so on. Like many of the groups here, as you can probably tell, I'm a big believer in experimenting with the vehicles, right? For me, this is an important piece of what we do. I don't really have a sense until that happens. So it works with a variety of those. And then our newest thing, which I didn't talk about today, is you could ask, some of you have probably been saying, look, if you're that keen, why don't you just combine these approaches? Why don't you actually use some sort of barrier certificate type scheme in your reward design itself and actually take advantage of some of the guarantees that systems like that give? So we have, in fact, built that. If you invite me back someday, I'll tell you a whole story about that. It's just an emerging story, so we don't quite want to say exactly what it does, but it turns out you can actually use a critic that's designed differently. And these videos, I guess I'm playing. I think you can see the robots flying. Sorry, I'm playing 6 videos at a time, and I think this is defeating my machine. But this is no longer in Vicon. This is with barrier certificates built in. We can go outdoors to buildings on campus, fly in environments where we basically don't hit obstacles. fly in the lobby of our building, a variety of other settings, and so on. So this is just late-breaking work. More to come on this. I just wanted to preview it. Okay, so I'll just conclude here. I didn't say anything about the size of the network other than just experimentally telling you they're small. But it is kind of cool that you can learn networks. The smallest of the videos I showed you had 20 neurons in them, right, running on each vehicle. So very, very tiny networks, right? They're performant in the context of the task we have in mind. Right? We have another line of work on systematically generating small networks by searching in network topology space, and you know that's an interesting area in its own right. And building simulators with basic physics, which have big sim-to-real gap with reality, can be rewarding in many settings for RL, for robotics, right? And, you know, 10 years ago, I wasn't quite sure how RL for robotics would look, right? But I'm more optimistic about it today. Now, there are others here who've been working on it for 3 decades. So, but I think there is a lot of promise there. You will get different mileage out of it in different settings, depending on what type of robotics problem you want to solve. But there's some interesting things you can do there, right? The simulator is available. If you look at our lab's website, you can get it from there and play with it. It might be great. You could just fork it and change it. So do what you want with it. And for those of you interested in this style of work, I know Coral is here next year, so many of us are looking forward to being in Austin. But if you want to come to LA next year, L4DC will be at USC next year. Keep us in mind, send your best work. And a relatively new conference called NEWS, which stands for Neurosymbolic Systems, is in year 3 of its existence. And it will be co-located with L4DC next year. And so if you want to kill 2 birds with 1 stone, come out to LA next year in June, and these 2 smaller conferences will be at USC. So I just wanted to leave you with that. And thank you so much for having me. I said there's a whole body of other papers if you care. I've listed them here, but they're on my website. So you can look at them. All right.
I don't know if we have some last minute questions. Peter, Garrett, there.
Probably your statement describes the reward, but how do you weigh? So basically, the reward is multi-objective.
Yeah.
Reward. So how do you weigh the different objectives?
We find the alphas. This was the question about how you find the multipliers. We search. We don't have a principled way of picking. Yeah.
Everything here, it seemed like there was K nearest neighbors.
Yeah.
But it breaks down when the number of agents gets very large. I just wonder naively, like, why not do a fixed radius and pull the state information? Maybe it's just too crowded and you're not getting all the neighbors you need. Like,
Yeah.
did you guys look
Yeah, that's a good point. A fixed radius would be great because it has the advantage that when the setting is sparse, you don't need to pay attention to anyone. Whereas with K nearest neighbors, you need to pay attention to neighbors even if they're very far away. So it's a little contrived in that respect. K is small for our problems. It's usually for a 100 robot setting. K is
big. The reverse, actually,
but
right?
yeah,
when things are dense, you need to pay attention to more.
You need to pay attention to more. That's completely reasonable. We haven't
built into the formula diagram, right? When you have more,
it is,
but the network architecture gets right.
It gets complex quicker. We haven't played with it, but there's good value. Good value. Yeah, no question. Yeah.
So within the set of people who've been working on reinforcement learning for robotics, there's sort of 2 camps. There's throw out everything we've known about robotics and go end to end reinforcement learning. That's all you need. Versus let's use reinforcement learning for little parts of the problem. Where do you see this work as falling on that spectrum?
So I'm definitely bullish for things like this, where simplified physics is known to use it, right? So it's a strong prior. The simulator, simple as it is a strong prior. Mm-hmm. So I'm very bullish on that for setting like this. Not the case that you can get that in all areas of robotics, but where you can, I think it pays off. So definitely that. Whether that puts me firmly in the second camp or not, I don't know. The end-to-end here, frankly, there are 2 aspects of this that I would confess are a little bit, they're a little bit because I wanted to play with them. One is this end-to-end business. do you really need to learn the 4 thruster commands? I mean, can't you learn to control the center of mass of the vehicle? There are any number of low-level controllers that know how to fly a vehicle. Come on, right? So I'm going to walk away from that.
So with that, we didn't try that.
No, we do it. Our latest system actually walks away from this. I just didn't show those results. So that's number one. And the second one is the second one is, do you really need to design this problem where every time you need to solve a problem, first you learn to fly, then you learn to navigate, then you learn not to, come on, that's not quite the right thing to do either. So we will slowly walk away from that as well. Those were more like, you could count them as like Gaurav playing with RL for the first time problems, right? They're not going to be, if I gave a talk in 5 years, I probably will walk away from this. They're interesting that we were able to do this in this way, but to me, they're not the most important thing here. I think for me, the more important thing here is the excitement that the right kinds of problems, you can go very far with the right kinds of priors in simulation. And large gaps between sim to real need not frighten us. They may, in fact, be our friends. And some foray that closes the gap between approaches that don't give guarantees and approaches that do. To me, those are the more interesting things. Less some of these other things. So I don't want to claim.
So you're not a full signer on to the bitter lesson though.
The bitter lesson is interesting, but here, we don't, bigger is not better here, right? Yeah. But it could be that this is all things considered, a narrow domain. As somebody said, full-scale helicopters don't collide like this and survive. So I might be making a little too much hay out of a domain which is narrow, and sometimes that happens. But I think there are still some interesting things here. Yeah.
We
may need to go. Sorry.
I know that
I have a
speaker has a call
Oh,
now
sorry.
at 12. that
Sorry.
has to join.
Thank you all.
Sorry about that, but we.
Thank you.